then we will talk about the histogram analysis, and then we will talk about the voxel size and volume, then resampling, 3D plotting, and segmentation. And with this, this is the URL which I have shared already in the chat window. So whoever wants to fork and execute the code together, they can do it. And with this, I will start my presentation. So basically, when we talk about medical image processing, DICOM is the standard in which the medical images are stored. So this is across the globe, and these DICOM images we get from the CT scans or MRIs. So whenever we go for any scan, the output of that particular scan is the DICOM image, and that is a very well established standard across the globe. So these are the table of contents for my today's presentation. We will start talking about the coordinate systems available for medical imaging and what are they. Then I will talk about the data which I'm using for today's session. Then definitely we will talk about what is DICOM in depth. Then we will see how these DICOMs can be converted to the Hornsfield units and what are Hornsfield units. Then we will talk about the windowing. Then we will talk about histogram analysis, as I mentioned in the agenda also. Then we will see that how to store the whole metadata available with the DICOM images in the data frame. Then we will talk about the voxel size and volume, and definitely we will talk about what is a voxel. Then we will talk about the resampling, then 3D plotting, how to plot the whole scan as a 3D. And then very important point is the segmentation. That will be the last point to cover with. So these are the libraries which we used throughout the session. And we will start with the coordinate system in medical imaging. So basically coordinate systems tells the location of a point or tells the location of the patient's body in the CT scan machine. So there are 3 types of systems available for the coordinate systems, and they are the world, anatomical, and the medical image coordinate system. Here for this particular session, we will talk about the anatomical coordinate system, and this coordinate system has the 3 planes. These 3 planes are axial plane, sagittal plane, and coronal plane. So when we talk about the axial place, you can think that a person is lying in a CT scan and the rays are going from the head till toes. So we will get the vertical slices of the scan. Then sagittal plane is either left to right or right to left. So if suppose the patient is lying on the shoulder or on the side, and we are getting the horizontal slices. Then the coronal plane is when the patient is sitting in front of the device and the images are from the front eyes towards it goes towards the back head. For this particular session, the images are available in the axial plane for this particular data set. So we will talk about, or we will just deal with the axial plane data. Now we will talk about the data. So this data is basically of the lungs CT scans, and I have taken this data from the one of the Kaggle's competition, that is OSIC. That competition data gives us the lungs CT scans of the patients which are diagnosed with the pulmonary fibrosis. This is a kind of disorder which nobody knows the cause and why it happens, and we do not have a cure also. And it creates a honeycombing kind of structure in the lungs, that is the scarring on the lungs. So basically, when we prognose the disease, it becomes more frightening for the patients because the outcome of the prognosis is can range from the long-term stability to the rapid deterioration. So patients can be stable for the long term, or they can rapidly deteriorate also. And unfortunately, the doctors also are not able to tell that where the particular individual will fall on that particular spectrum. So that is more scary part for the patients, and that's where the data science can help, or data science is expected to help for the predicting the deteriorating conditions of the patients. So details of the data can be found here. I have attached a link over here. Then we will start with the processing of the data. So these are the different parts where we get the data. Here I'm loading the CSV file in the plain pandas. Then I found some duplicates, so I just removed those duplicates. This is a very simple thing. Here it is. The data looks like, so this is the training data, which contains the patient ID, then the weeks. So every week, or for a particular frequency of the weeks, the observation is taken, and this is the FVC. This is forced vital capacity. That means the amount of air that a patient can blow out as soon as possible. Then this is the percentage of that value, age, sex, and smoking status, whether the person or patient was an ex-smoker or current smoker or non-smoker. Then we will talk about what is DICOM. So if I'm going fast, please let me know, because we have to cover a lot. So I'm just rushing down on the basics of this session. So this is the DICOM. What is DICOM? So basically, DICOM is a standard this DICOM image file is the outcome of digital imaging and communications, which is represented as .dcm. So this system, or this particular system, is so easy to integrate and continuously evolving that it has become a standard across the years worldwide. So how this DICOM differs from the other images is that DICOM actually group the whole data and group the whole metadata in the form of header and then the data sets. So it consists of a header and then the data set, which we will see actually how this DICOM looks like. And there is a link shared, which says that what is the how the DICOM came in the picture, and what information we basically provide as a part of the DICOM. So more details about the DICOM is here. And then I just attached one video. This video shows very described in a very described manner about the CT windows, levels, and density. If you have not seen this video yet, I really recommend to watch this video. This gives a very clear picture. Then I'm loading the DICOMs, or so we will use the term scan and slices. So scan is basically the home or the whole CT image, and slices is the every 2D image of the scan. So basically here I'm loading the slices of one particular scan. So one patient, if they are undergoing the CT scan, then they will get a scan. And if it is an axial plane, so we will get the slices of the lung. And if we combine whole slices, then it becomes a whole lung picture. So every scan is made up of multiple slices. Every slice is 2D basically. Um, and completely they makes the whole lung. So this method is not doing anything great. This is just it is returning. It is Okay, so this is the library. PyDICOM is the library available with the Python, which helps in reading the DICOM files. And DCM read is the API, which actually goes to this particular path, return all the slices uh, in a list. So slices is nothing but the list of all the slices or all the 2D slices of a scan. Then I'm sorting them based on their instance number, because the slices, so when we plot on the 3D, those slices should be in the sequence order. So this is the load slices I have loaded for this particular patient, and here I am going for the first slice. So here is the first DICOM, first slice of the DICOM image, and this is how it looks like. So we can see that this is the differentiating point of the other images than the DICOM, because it contains lot of other metadata. Contains a lot of other metadata. So this is grouped in the different headers. So this, if we see 0002 is the altogether one group, then 0008 is the another group. So that's how they are grouped in the different categories. So we because we do not have time to go through each and every metadata, so we will just glance through the metadata which we normally use for the processing of the images. So first thing is that we will talk about the slice thickness. So this is the slice thickness. Slice thickness is basically the distance between the two slices, and this slice thickness is further used for getting the volume of the image or volume of the lung. Then we will talk about the slice location. So basically, slice location comes in the picture, slice location or image orientation of the patient. These two tags come in the picture if the slice thickness is not given in the data set. So if sometimes some metadata can be missing. So if the slice thickness is not given, then we can just take these slice locations of any two slides and minus them. So we will get the slice thickness or between the two slices. So that's where this metadata comes in the picture. Then rows and columns is the number of rows and number of columns of the image. Then pixel spacing, it is a very important metadata. This gives the pixel size, X and Y coordinates. Pixel spacing is nothing but the pixel size. Then we will talk about the window center and window width. These are again very important parameters, and we will talk more about window center and window width when we will discuss about the windowing. They basically help us to give the region of interest out of the whole image, because we do not want to focus on the whole image. Every scan is for a particular part, and we want to just focus on that particular region. So these two parameters help us in getting that information. Then rescale intercept and rescale slope. So rescale intercept and slope is used basically for the linear transformation of the pixels. Why we need the linear transformation of the pixel? Because when we stored the pixels are stored on the disk, and then we store on the memory, there is a linear transformation, and to get that transformation from one medium to another medium, we need to convert the pixels, the raw pixels to this we need to do the conversion, and that conversion is just a plain linear transformation. How we will do that, we will see later, and that conversion is nothing but the conversion into the Hornsfield units. So we will talk later about these two parameters more. And then this is the pixel data. So pixel data is just an array of the actual image, and this is the data which we will use to plot the images. So this was all about the metadata of the DICOM images. Then we will talk about the conversion of the Hornsfield units. So let's talk about what is actually Hornsfield unit. This is named behind the scientist who discovered this. So this is basically the quantitative scale which actually provides the accurate density of the type of tissues. So on every image or on every X-ray or CT scan, there are different densities. In the X-rays, only we had the 5 type of densities: air, fat, soft tissues, bone, and metal. But in CT scans, we have a huge range of densities. It starts from uh, which we take into the consideration. It starts from the air and it goes till the bone. So basically, the range of this whole window from air to bone is -1000 till 2000, sometimes 2000, or basically normally we consider it till 1000 only, till +1000. So basically the scale is the standard of the scale is water, which is represented by the 0 value. So we need to understand that this household unit basically gives the density of the tissue. So how we see is that, so water is the standard. Anything which is lighter than the water will have the negative densities. That means it will be the negative Hornsfield HU. For Hornsfield unit, I will use the HU term. And anything which is denser than water will go on the positive scale. So when we go towards the negative scale, the gray scale becomes going towards in the blacker shades, and the air is of the black shade. And as we go towards the positive or denser side, that becomes the whiter on the mm, grayish or white side of the white color, and the bone is of the white color. So it is in between black and white, all the gray shades. So basically, these are the standard HUs which we consider. So for air, this is -1000. For lung, which we will use for later, -500, or we can take -600 or -700 also. Fat, -1000 to -50. Then water is 0. Then blood, 30 to 70. Muscles, 10 to 40. Then liver is 40 to 60, and bones is 700 to, sometimes very dense bones is 3000 also. Then we will see that how this conversion is happening. So this is the first step of the processing of DICOM processing. This is the very first step. We have discussed multiple things, but this is the first step which we are going to do. This is the conversion to HU. So we discussed about that this is a linear transformation. So we will just take the slope, multiply all the slices. Every slice we take one after another slice. We take it, we multiply it with the slope, and then we just add the intercept to this, and it returns the array of all the images of a particular scan. So this is the conversion of the HUs. Now we will talk about the windowing. So basically windowing is, if I show you one scan quickly, yeah. So this is basically one scan, original scan. And if we see, there are many other things apart from lungs, which we actually do not want. Okay, so what happens is that, okay, where we were, yes. Yeah, so we were on windowing. I would prefer to go. So windowing basically is the process where we decide that what is the range of the grayscale we need to approach or we need. So basically it gives the region of interest. So when we just saw about the lung scan, the lung was very small amount of lung was there, and lot of other things, black things was air and white things was the bones. But we are interested only in the only in the lung. So basically this windowing gives the region of interest, and how it gives using the two parameters, that is window width and window level. So window width, what is window width? Window is the grayscale which can be displayed on the image. So we do not want the black color because that is the air. So we do not want that density to show. So we adjust these grayscale range so that we can just get the only the lung portion of that. And window center, which is known as window level also, that is just the center of that particular range of window width. So for an example, uh, uh, for our case, the lungs window width is 1500 and window level is -500 or -600 as we discussed. So if we take the range for this particular window width, then we will get the range of 150 HU to -1350 HU. How we get this is the method how we get this. And you can go through more about the windowing in this particular link, and how we actually get the window width and level, that is briefly described in this particular article or in this particular topic. So what we are doing with this method is we are passing the HU image. That means we are not passing the raw image, we are passing the HU converted image. So first step was we have converted to the HU, and then that image we are passing here along with the level and the width. So here minimum value, we are just doing the level or center minus width divided by 2, and maximum we are just adding them up and divided by 2. So anything which is below the minimum value, we are setting it to minimum value, and anything above the maximum value, we are setting to the maximum value. So basically we will get only the grayscale range, which is in between this minimum and maximum values. We will see the usage of this particular this particular method later. Now we will go with the histogram analysis. So we have gone through the DICOM conversion to HU and then windowing. Then we will talk about the histogram analysis. So histogram analysis, we all know about the histograms, and I have just plotted the histogram of two images, two images. One is the raw pixel area and another is the HU converted image. So we got the raw scans here. So what we are doing here is we are taking the first patient, we are loading the slices in the scan, and then we are rescaling them, that images into the pixel HU, and that's what we are plotting here. So if we see this plot, the raw images, that the it shows that -2000 there is lot of values which goes to -2000. Then it shows that there is no air, no lung, nothing is there, and then a lot of water is there, and some fat, muscles, and then bone is there, lot of bone. It shows lot of that too dense bones. But when we convert it to HU, it makes more sense for us, because whatever was less than -1000, we are not bothered or we are not concerned about those values. So we have put the 0 here, so nothing is there. So a lot of air we can see in the graph that I will show you later, that there's a lot of black regions around there. So a lot of air in the images. Then this -500, it starts with the bone. Sorry, it starts with the lung, and then it goes, and there is some bone is also there, A bone starts from 300 to 500 and so on. There is some fat and muscles, this 30 to 40 range. So this makes more sense. So this is the histogram analysis. So we can see that actually what is the range of the HUs in the our images. So sometimes it goes like here, it is going till 2500. So for very dense bones, it goes to that level. And for metals, it goes till 30,000 or something. So if it goes beyond that level, beyond 2000 or 3000, that means it is metal. We can suspect that there is a metal. Now there is a small utility method which I have just written to store this whole metadata into the data frame. So this is simply taking all the metadata. So this is nothing but the function to get all the DICOM parameters, converting them into the dictionary and give it back, except the pixel data, because we do not want to store the images in the data frame. Pixel data is the tag for the image metrics. So this method is doing nothing but it takes all the parameters of the image and stored in a dictionary. Then there are few parameters which we manually calculate and want to store for the further usage. So this is the minimum value of the image, raw image. This is the maximum value. This is the mean, standard. Then max minus min to get the variance of the image pixels. Then this is the row and column which shows the pixel which we are taking the pixel area basically. So we are multiplying the row and column. Then we are taking the image area. Then this is the row distance covered by 1 pixel and column distance basically. So here we will take the area of one slice and then volume of the slice. So area is simply row distance multiplied by column distance. But when we get the volume, when we try to get the volume, here we need the slice thickness, because a volume cannot be taken for the 2D objects. We need the 3D objects for getting the volume. So here the slice thickness comes. So we can think about a pixel which has the X and Y coordinates, and the Z coordinate will be the slice thickness. Okay. So everything we just store. And here I have just kept this whole data frame in the form of a pickle. So later, if I want to use this data, I can directly load this pickle. I need not to process all these things to save time. So this is the data frame, how it looks like. It has lot of metadata. Will not go through the each of the metadata. Now we talk about the voxel size and voxel volume. Basically, so what is voxel? Voxel is nothing but the 3D image of a pixel. So we have the pixel spacing as X and Y coordinates. So that and Z coordinate will be the slice thickness. Okay, so that's how we can visualize that the pixel, the 3D form of the pixel, and the 3D form of the pixel is known as voxel in the medical terminology. We have calculated this voxel size and volume in the metadata. Here we have calculated already. This is the slice area and slice volume. Okay, we have not calculated the voxel area. Voxel volume we have not calculated. We have calculated the slice area and slice volume. So here I'm just plotting 4 graphs which shows the rows, columns, the pixel rows, pixel columns. That means the rows covered or distance covered by the pixels, and then columns and the slice area and slice volume. So if we see this, there is a lot of variance between these values. So we will quickly see the volume because as per one of the document, it was referred like volume is very much related. It has a very good feature to capture, and it is related with the FVC values also. So this, if we see the volume of the scans, then it varies a lot. So different slices have a different volumes. So does it mean that the slice of a bigger volume will have the bigger lung size? No, definitely not. So this is not the uh, definitely, certainly it is not like that. So what is that? Let's see. So I have just taken the minimum area, minimum volume of a scan and the maximum volume of a scan. So if we see in the maximum volume, there are a lot of many other things apart from the lungs. So these are the lungs basically, and there are so many other things apart from the lungs, which we will see that what to do with this extra values or extra noise. And here we will see that the only the lungs are there, other data or other things are very minimal. That's how the volume is changing of the slices. So now when the volumes is changing, another one more thing is that we will talk. So just see quickly that this is the slice thickness I have taken from the metadata data frame which we created, and these are the unique values available for the slice thickness. Now we can see that for some of the scans, the difference between two slices is 1.25, and it goes till 8, or for some slices the distance between the two slices is 0.8. So there is lot of variation between the distance of the two slices. So if the distance between the two slices is different, that means the slice thickness, if the slice thickness is the different, that means the voxel size of the images is also very much different. And if the voxel size is different, then the data which with this difference of the voxel size, if we will feed to the CNNs, then definitely we will not get the good results. So to get rid of this particular problem of different slice thickness or different voxel sizes, we do the resampling here. So till now, we have seen the conversion to HU. Then we have seen what is the DICOM conversion to the HU. We have analyzed the histogram, that what is the range of densities of different tissues our image is having. Then we have covered the windowing part. Then we have seen how the voxel sizes and accordingly their volumes basically varies from such a small volume to such a high volumes, and why these volumes are different and how to treat this different volumes, basically this difference of the slice thickness. Not only the slice thickness is different, if we will see, there is a x and y coordinates are also different. See, we can see this is the spacing I have just printed. So for one particular slice, the spacing is 0.6565, and the another is the size of the pixel in x and y coordinate is 0.79, 0.79. So basically all the pixels are of different sizes across the scans. So here we come with the concept of resampling. So basically, resampling, what it does is that it takes the new scanning parameters. So suppose we want to convert the whole scan into 1 millimeter by 1 millimeter by 1 millimeter, then the whole scan will get the new scanning, and with the help of the resizing factors, we will convert the whole images to the new scanning provided. So how we get this is, let's see. This is how we are getting the resample. So basically what we are doing is that this is the existing spacing, slice thickness and pixel spacing. So this is the three values in the spacing. So this method actually takes the image and the scan. So this image is nothing but the HU converted scan, and then this scan is the original raw value, and this is the new spacing. This is in in terms of millimeters. So what we are doing is that we are taking the new spacing, then whatever is the new the old spacing, sorry, we are taking the old spacing or existing current spacing, we are dividing it with the new spacing, so we will get a resize factor. Then we convert the image shape, existing image shape, to the resize factor, so we will get the new shape. We will just round it off, and then we will get in terms of the, so this is in terms of the pixel, so in terms of the shape or the whole image, we will get the real resize factor, and then we just put this, and accordingly we will get the spacing, also new spacing, and that we will input in the, already there is a API in the Skype library, that is the interpolation, and we will zoom it, use the zoom API with the actual image and the real resize factor. So we will just provide these values and we will get a new image and the new spacing. So here I have just plotted, I have just printed, this was the original shape, and after the resampling, this is the new shape of the image. Okay, there is some problem. Give me a minute. No. Okay, there is a problem with this plot 3D, but another method is working. So after this is the resampling. So after resampling, we will just do the 3D plotting. This 3D plotting, that is a very standard way which uses the marching cubes algorithm. I have put the references for how this marching cubes algorithm works. And this uses for 3D, for 3D, it takes the poly 3D collection. So this is a method I have taken from one of the other references. This is a very standard method and I have used the same thing. So, and here, this is the plotting of the hue scan. This is the plot of the hue scans, and this is how the 3D plot looks like. But I'm not very much keen for the resampling. There are few reasons we will see at the time of segmentation, that how resampling can be maybe replaced by the resizing, but that we need to see. But at the time of segmentation, we will see what is the problem with the resampling. So this is the graph and this is the segmentation. So this is a very important topic, and this is a very important process during the medical image processing. So segmentation, basically what it does is that first, this is the another part of the extracting the region of interest. So with the windowing, we got the range of grayscales which we need. But that grayscales basically extract the lungs as well as other portions or other tissues also, which comes in that range. But when we want to give it to CNS, definitely the CNS will work better if we just can give only the lungs rather than giving the windowing image. So if we see here, these are the, this is the scans of my first patient. These are the different slices of my first patient scan. If we see here, there are, it starts because it's a axial plane images. So the lung starts here and it goes to the full capacity and then it goes towards the end. And if we go for the segmentation part, then this is how the segmentation work. We can see in these images, only the lung portion of the images is given to the CNNs. So basically, after windowing, what was happening is suppose for this particular scan, if we want to window it, then it will give this much portion probably. It will just remove all the air and it will remove all the bones. So so many, but many other tissues will be there as the part of the scan. But segmentation will actually gives only the lung portion. So definitely CNNs will work better if we can give only the region what we are interested in. How we are getting it? So this is how we are getting it. Yeah. So this is the normally set procedure, how we do the segmentation part. We normalize the images first. So normalization normally means the take the mean and then divide by the standard deviation of the image. Then we cluster it. So we all know that clustering is the best technique to group or group two things or more than two things. So that's how we will use clustering here. Different type of clustering we can use: the k-means clustering, hierarchical, or mean shift clustering. I have used k-means, and there are other clustering also which we can try on. That is fuzzy clustering, because the borders are very fuzzy. So normally fuzzy clustering is also very much gives very good results also for the segmentation. And this is here is the link where we can go more about the segmentation. Then after the segmentation, after the clustering, we just take all the centers and get the mean and get a threshold image. By using that threshold, so all the clustering centers, mean of all the clustering centers we use as a threshold, and anything above that we mark it as 1, and anything below is we mark as 0. So it is something like a binary image we will get after this threshold application. Then we will do the morphology. We will do the erosion followed by dilation. So erosion is basically the contraction. So by using the erosion, we will remove all the unwanted parts of the lens. And then we will do a bigger or large dilation so that we should not clip any part of the lung. Then we will label the different regions of this lung and color them with the different colors. Then we will create the lung mask, and with the lung mask we will apply that mask on the original image, and that's how we will get that segmented part. So let's see how. Give me a minute. Okay, so it didn't execute it till here. I want to basically show the after the segmentation part. Okay, this let's run it whole. Maybe by the time I will finish the segmentation explanation, that should work. Or if I quickly see if I have got here. I know that is a problem. I'm sorry for this. I will check later if time permits. I will check later for the new, older version if I can show you. So what we are doing, let's quickly wrap this last topic. So here, as we gone through the steps, we are normalizing the image, then clustering, thresholding, morphology, labeling. Then we are creating the lung mask and then apply the mask. So here, these are the steps. Here we are just doing the normalization of the image, mean, then standard deviation. We subtracting the mean and dividing by the standard deviation. Here we are taking the middle of the image so that we can perform the clustering better. So what we are doing, we are taking the middle of the image to perform more better clustering. Then here I have used the k-means clustering so that we can cluster the lung area with the anything else or apart from the lungs area. This is the implementation of the threshold, where we have just implemented the thresholds, which converts the image into the binary zeros or ones. Why we need that is also because morphology always work on either the gray images or the binary images. Then we apply the erosion followed by dilation. Then measure is a library available with the Python. We are labeling the dilated image. So we will get all the different regions, and then we are making the boundary boxes for that particular regions, and that's how we get the mask after this. And that mask we do one more times of dilation, so that we should not clip anything, any part of the lung, and then we apply that mask on the image, and that's how we get the masked image. Okay, so basically I think, okay, so there is the closing brackets are missing, that's why that's a problem. Okay, so anyways, we will see just now that how the segmentations look like. So basically, this is just a utility method for plotting the stack. And that's how the stack looks like. The original stack looks like. So this original stack, we did the after getting the resample, and after converting it to the hue images, this whole stack, we applied the segmentation here. So this, if we will see this, I have taken the image one, and image one was the outcome of the resampling. Here, image one was the outcome of the resampling. Okay. So here we see the slices, number of slices was 31 actually originally, and then it becomes the 39 after the resampling. So here we see some of the things which actually some of the places the segmentation is not working properly. So suppose first we will see that these images, when we applied the segmentation, we actually get the actually only the lung portion, which is great, and this is the required thing. But if we will see the scan slice 10, this slice, if we see, and if we see the original slice 10 here, then this segmentation actually missed some part here. This lung is much more bigger than what we get out of the segmentation. This is a problem which I need to fix. And then we see this a few more slices got introduced after resampling, and I am just assuming that the slice 11, 12, and 13 are something like that, because here if we see 11, 12, and 13 are quite different, totally different. And if we see here the slice 11, then it looks more similar to the slice 14. And then it continues to go. So this is one problem which I suspect um, segmentation, of course, is having some issues, and along with that, the resampling also created some extra slides. So these are the slices which I'm assuming is looking like that. So that's how, but we need to definitely try out with the resize. So I'm not very much keen with the resample thing. But definitely that is very, very important, because we need to make all the pixel size of in a proper format, or of the um, synchronized sizes. All the sizes should be same. Here I have written the code which actually incorporates everything together, and it is implemented on the whole data. I have taken only till for the 10 patients. If we will remove this particular list, then it will be executed for the whole patients. So what's happening here, that I'm just loading the slices for all the all the patients one by one. So this whole process I'm running for all the patients, and then I'm converting it to the HU. Then the resampling is happening, and then we are applying the windowing just before the segmentation, and then we are applying the segmentation, and we are appending it and storing it to the NPZ format. So if we want to, NPZ is just a compressed format for storing the images. If we want to store it in the PNG format for all the patients, then you need to just remove these comments and this comment and comment out this line, and you will get in the PNG format. So that's what is all about my session. And these are the different references I have gone through, and notebooks, which are really, really helpful for making the session and for all the DICOM processing information. So now we are open for the questions. We have 5 more minutes.
Niraj, we have one question from the YouTube chat from Samil asking, could you explain why were new slices introduced after resampling, and how can we improve results of segmentation?
Yes, because we have resized it. See here. Because we multiply the whole image with the resized vector, so accordingly all the slices also got new introduced here. Image shape multiplied by the resize factor. Resize factor is the 3 values which makes the slice thickness and pixel spacing. So when it multiplies with the image space, image shape is also the 3-dimensional one, and this is where we get it introduced. Because of the resizing, it got introduced. That I hope that answers her question.
There's another question in the chat from Alan Coppola. What are
I'm
the
not
visual
able to see the
features?
chat actually.
Oh, you see it? Great.
Okay, can you read out for me, Mia?
Of course,
Sorry,
yeah.
I'm not able to see the chat.
What
Yeah,
are the visual features that you are looking for to capture the disease?
okay, now I can see. What are the visual features that you are looking for to capture the disease? Okay, so visual features basically for this particular disease, because we are focusing on the lungs, we will go for the histograms, all the histogram values. That is one thing. And then these are the segmented images is the another features. Then resampling resized images is the another feature. Then volume, lungs volume is definitely for this particular problem. Lungs volume is another feature which we will capture because that is very much related with the FVC. So these are the typical features which we are capturing for this particular disease. And area also, area of the lungs. Yeah. Post the link again. I joined after this. Okay. Let me see if the previous version I can show. I have 2 more minutes. If I can show the previous version. Yes, this is working here. So this is how the segmentation works. Uh, yes, I'm still sharing. So I have 2 more minutes left over. Quickly, I would like to show how this segmentation is working. So this is the original image, and this is how after thresholding we get the black and white. Then this is basically the after erosion and dilation, how it looks like. This is the after labeling the colors. Then this is the final mask. So when we are creating the boundaries, there is something going wrong and we are missing this particular last one piece of the lung here. And that's what goes wrong with the final image, final after applying the mask. So this is a problem right now, which I need to fix. Yes, this is how this I really wanted to show to have a better understanding about the segmentation. Yes.
And there's one last question. I don't know if you saw it, Niraj, also from Alan. How do you then synthesize a plan to detect or non-detect disease using deep learning?
Sorry. Can you repeat it again, Mia?
Sure. How do you then synthesize a plan to detect slash non-detect disease using deep learning?
It should detect or not detect. I didn't get the question still. Oh,
I sent it to you in the chat if you want to try to read it there.
yeah. Could you explain why were new slices
Oh,
introduced after reset? No,
no, this one. Sorry.
this was yeah. Could you please explain why were new slices introduced? This is the same question. Okay, how do you then synthesize a plane to detect non-detect disease using deep learning? How do you then synthesize a plan to detect? Okay, so basically, this is the images, segmented images. Now they are ready to feed with the deep learning, and for this particular problem set, we have to predict the FVC values for the next few weeks, and based on that FVC values, we can actually see whether the patient's problem or patient's condition is deteriorating or not deteriorating. So what we will do is that there is a different kind of CNN algorithms which we will feed this data and try to predict. Basically, this is so we will try to predict the FVC values, and that's how we will see then we will relate that FVC values with the degree of the seriousness. So this is this is just the processing of the images. This whole data set, what we saved at the last as .npz, that needs to be fed with the deep learning algorithms, and then we need to work on it. So this is just a half portion of the whole process. So that's what I have to present.
Thank you so much, Niraj. We are out of time. I want to thank
Yeah,
everyone for joining. Thank you, Niraj, for hosting. This was great.
yeah,
And the video will be available on our session page where you joined, and also on the YouTube channel as well if you want to reference it. I also want to mention that there was a related panel earlier this week called Deep Learning in Medical Imaging, and it might be a nice complement to this more technical session if you wanted to hear a little bit more. So thanks again, everyone, and we'll see you soon. Thank you,
yeah.
Niraj.
Thanks, Mia. Thank you, everybody, for joining.